Um, okay, so welcome to second week. Last week we learned about basic chemistry, which was recorded. So I hope you watched that on YouTube. Um, and then also we learned a little bit about mass balance. And today we are going to extend that mass balance equation. So that's chapter one. But before that, I wanted to make sure that we all know how we can interact with each other and have this class more discussion oriented. So that's why usually what I do is I register all of you to either Piazza or Campusware without asking you, and then I ask people to opt out if they don't want it. This time I didn't do it because I realized there is a link I can send and you can join. So I send you that link by email. So I'm going to share that screen so that you know what I'm talking about. So if you see, this is the Campusware feed that I see, and 114 students are invited to register, and I think 114 is registered. But our class is more than 220 students or around those range. So I'm sure that a lot of students have not registered. The reason why it is important is because I prefer you not email me, because if you send me email that I respond that email, then that's only you and me know. Everybody else didn't know anything about that, which is not very helpful for rest of the class. So I think what you do is you can send question anonymously if you don't want to be known to the rest of the class. So here is the platform where you should any questions related to homework, anything, you should ask those questions. For instance, here this is a question asked. I don't know who asked it because the students chose to be anonymous, which is fine with me because really it's all about discussion. So that's the reason, that question was one normal sulfuric acid is what molar H2SO4. For some reason, the student says that no, this is a number C was the correct answer. That's the what I wrote. But I don't think that's the correct answer. I know that correct answer is zero point 0.5 mole. But maybe it's a mistake I made when I was writing. So I will check that. But again, this is how, when the student asks this question, it benefit the entire class. So really, it will be nice, or it will be important that you ask questions on um, anonymously or anyway, directly. But if something sensitive, then of course you should send email. But any questions related to class or clarifications about the materials, I think it's much more helpful if you ask on Campusware. Again, any personal question, any other sensitive issues, you should send me email. Okay, I'm not replacing email. It's just I've had time um, connecting with a lot of students by email. I will miss more likely if you send me email. But if you post it here, I will not miss it because everything is there. No, it's not buried. So how do you register? Um, in the chat window, some student already answered. Courtney, thank you. What's the password is 3636. That's the password you need to use. Again, go back to the email because I sent via my UCLA. So you should have that email. If you search, it has the link as well as the code. Same thing for YouTube. I know that somebody asked about YouTube playlist, and Amos replied that. So that's the playlist. You should bookmark it, or if you don't have it, you can go back. Again, you can ask the same questions on ClassSpeed. So if you go to the ClassSpeed, if you see ClassSpeed, the announcement I put it here now. If you see week one announcement, I have the YouTube playlist here. So you can always come back to these locations and find all this information. Um, so I'm posting it here, most of them. So I didn't read many of these comments here, but I would read. Is homework graded on accuracy or completions? So here is a trick. The homework one is not graded for accuracy. This is only applied for homework one. This is because this is a background. I'm not really looking for whether correct or not. But homework two and everything else would be graded by grade scope. So that's why that will have at least some degree of accuracy. But homework one will be mostly graded for your effort. So write, submit whatever you think. So we'll randomly check a lot of the questions and see where the students struggle. But you should not struggle. The reason is we have lots of office hours as well as online. Same thing or on campus where ask those questions if you have struggle. So my hope is that you submit the homework with everything answered properly or correctly. If you have difficulty or if you have doubts, ask those questions. And again, I this is a video I uploaded with a more campus, more questions on mass balance. So this is just I upload in the morning. There are four more questions. Those were on the slide, but I never solve it in the class. So my idea here is that anything on the slides and I don't solve it, I give you some time to work on it. And after a week, or not after a week, within 3 to 4 days, I will upload the solutions. So don't watch the solution until you try. So that's important. In exams everywhere, you will not learn much if you just look at the solutions. So there are five more questions here, or four more questions. It is processing still. I'm trying to see if it is okay. It's probably done. So as you see, I didn't bookmark yet because I just uploaded it. The quality is not good because it takes some time to upload the final versions. So if you click on different locations, it will tell how that question is solved. So this is another questions. So you can keep going, and there is another question here, question number 4. That's the textbook problem number 15 on chapter 1. Um, that's again everything is solved here, so you should be able to find. Then there is another final questions, textbook problem number 19. So I solve it here. So you see there are four more examples, and so all these are going to be helpful for you to answer any questions on homework number 2, which will be released on Wednesday. That will be all on mass balance. So I really encourage you to solve.
Professor,
Yes.
I didn't mean to interrupt. When I'm navigating your YouTube channel, you have like, lecture 1A, B, C, D. Are those all your lectures throughout the week, or are those some of those discussions for specific discussion groups?
No, so everything I upload here are nothing is from the, well, let me put it back. So this is everything I recorded, means it's nothing to do with the TA. If you are distinguishing from discussion session by TA, I don't upload them here. Those are on CCLE. TA uploaded, so you should be able to access those. These are mixed of live lecture as well as the discussion that I do recordings. Uh, so everything live lecture will be recorded here or posted here. Everything I do after the class, for instance, example, those are the questions I record after the class. I'll post it here. The reason there is a little bit delay for the recording for the example is for you to try. But I'll cover most of the class materials here in the live lectures. Does it answer your question?
Yes, thank you very much.
Thanks. All right, so I would now stop the share, and also, okay, so lecture 3 will work more on mass balance, but more specifically about reactions. Last time what we solved, there are some reactions, but not necessarily details. When I say reaction, because we are interested in chemicals, and chemical react naturally in a system. So you wanted to know how to account for reaction in your mass balance equations. So again, just to highlight, these are the questions on CCLE. You should be able to answer those. Please answer, because these are for assessment. I'm not grading them. This is just for your own learning. But I looked at it, how many students do answer correctly, or how many trial it takes to get the correct answers. That way I know if let's say 50% of the class has struggled in one questions, then I would try to try to find a remedy for that. So these are all for my assessment. You should take those quiz. Announcement: homework one is due on Wednesday. So that's you should have started already. You still have 2 more days to solve them, but you have only one discussion session. That's on Wednesday. So you should ask any questions on that, or you could ask questions after the class today if you have any difficulty, because second half of this class is office hour, for you to ask me any questions. Readings for this materials, mass balance. As I said, this is the page number 2 to 21. That's the handout on chapter 1. I expect you to read it. It will help you improve the understanding. Um, Also, I want to say that when I say I expect you to read, you don't need to read. If you understand the slides, you are good enough to answer the questions on exams as well as homework. But if any places where you feel like you still don't understand, you should read the textbook. Um, but in general, if you're reading the textbook, always helps. But if you have not read it, still you'll be able to still answer the questions based on the slides if you understand slide. Again, a learning objective. Today you are going to learn how to include reaction terms in your mass balance. You learn how different types of reactions are, some basic understanding about what is reaction rate, what is the order of reactions, what's the unit of rate constants, how to use those, how to interpret them, and so those will apply for the real world problems. And more specifically, we'll solve some question on unsteady state, because in nature most of the time it's not steady state. Things are changing over time. So you are interested in to understand how long it takes to change back. Again, we are more focused on reaction today. Next week class will focus mostly on energy of mass balance. So what's the reaction applications? So think of this, if you search any chemical spill, go to Google right now and search it. That's what I did yesterday. I search Google, every day, every month there are some news about spill, contaminant spill. No matter how much we are careful, there are always accident occurs. This is one of those accidents in Mars Creek Lake in Philadelphia, not Philadelphia, Pennsylvania. Um, that's why there is a pipelines which is accidentally release lots of gas chemicals into this lake. That lake is used for recreational purpose on the extreme left, and as you can see, this lake people also fish there, fishing. So anytime there is a contamination, there is a concern. On the extreme right side, if you see, that's the Pennsylvania Turnpike. That's the biggest, one of the busiest roads, Route 76. So that goes near the creek. And there was the pipeline was going actually a little bit inside the lake system or towards the lake system. So that's why there was an accident. So they are protesting, or they are saying that you should change the pipeline towards that road so that it doesn't really intersect. But either way, so anytime the accident happens, the first reaction is, oh my God, no, all this thing happened. What will happen to our world? The fish is going to die. Is this toxic? Is this, how long this or situation will prolong? So these are the questions as an engineer you will have to ask. So the question is, first thing, if you are in a consulting firm, you will be contacted by state agency. They will say, "No, can you give us estimate about what's the concentrations of pollutant in the lake?" Because that concentration determine whether the fish will die or not. And the second thing you'll be doing is, is there um, any degradation of the pollutant naturally? Because if there is a degradation, that means the lake will clean by itself. But if not, then you have to take some remediation actions, like you see in these pictures. They are trying to absorb that contaminants in a different lake. This is not the same pictures or same lake. Then once you know the concentrations, you'll talk to the people who are specialists in toxicology. They will say whether this is an imminent danger for fish or the people. So they will have a warning sign. And once you have done those pre-assessment study, you will be asked to say cleanup effort if there are too much contaminants. So as an engineer, you'll have to develop some methods. Sometimes it could be physical process, sometimes it could be chemical. For instance, here they are just basically absorbing everything float on the surface because oil float on the surface. So you just have to get a big scrubber and just try to concentrate them on the surface, and then you take them out. Okay. So then once everything is done, your goal is to prevent this kind of accidents to happens again. So you'll be also asked to provide your expert opinion about what could be the better way to manage this kind of system. So you will do risk assessment. Say, okay, this pipe burst here. It's too close to the lake. Let's put it somewhere here, and then these are the measure we should take so that this accident should not happen. So again, these are all reaction problems. The very first thing is estimate the concentrations of pollutant in the lake. That's what we are going to learn in this class today. Okay, um, so that's based on the reactions. So when you say reactions, as a chemical engineers, most of the time we think of a reactor. Reactor happens, but when you think reactor, it's not necessarily a very defined um, enclosed space. It could be open system, it could be many things. So as an environmental engineer or scientist, we call lakes, rivers, any water systems as a reactor. We just have to create our own boundary and then we have to solve it. So that's why I say, if you see here, these are the, one of the things over here is this is a river. So it's flowing. I don't know which directions. Let's assume that it's flowing down this side now. Um, So that's a reactor, but it's a flow reactor. It's continuous flow reactor or block flow reactors. And then if you see, this is a storm drainage, so that storm drainage is moving all the water outside here. So we can call this is also a reactor or the storm reactor. So this is storm water. So this is also a flow system. But at the bottom, that's a pond. Okay, that's a pond or lake, what do you call it? So let's say this is pond or lake. Okay, it's very difficult to see where is the flow here. Okay, but there is a flow. The water doesn't come naturally here, or it doesn't come out of blue. There must be something coming in. Either it's rain or it's whatever it is. There is a flow at some point that accumulate water here. So that's also a batch system. So we'll learn about all that. So anytime we think of reactor, we divide into two things. Number one, two type of reactor. Either there is a continuous flow or block flow reactor, which is pipe, wetlands, river, where things are moving at one point to another. So that's a block flow reactor. Anything that not categorized by that, if we call complete mixed system or lake or pond, that's basically enclosed space. We can call batch reactor, but complete mixed system means, what I'm saying is complete mixed system means, if you have a batch like this, complete mixed system means if you take a sample here versus here, it really doesn't matter. It's the same contaminants or the concentration will be same. Why it is important? Because, in a reactor, if things are moving in here and leaving out system here, so the out, C out is always, it makes it easier for us to assume C out equal to C or any times in the system. That way you can solve the equations. Not necessarily always it has to be the case. Only case when it's completely mixed, you can assume concentration of contaminant in lake would be same as concentration of contaminants leaving the system. That means completely mixed system. Okay, that's the assumption. Otherwise, there are two types of reactor, as I said here. So now that you understand how to connect natural system to reactor, this is what the picture of reactor look like. Now this is a illustration purpose. It could be lake or pond. Okay, we call batch reactor. The difference between this and the second one is the flow. There is no incoming flow. You just dump everything here and things change over time. So usually batch reactor is an unsteady state reactor. Means, there are not continuously things coming in, so that means if there are things will change inside the system because of degradations. Complete mixed flow reactor means it's a batch system, but it has incoming flow and also outgoing flow, which is the case for many ponds, where you have a pull up water and then things are coming in and leaving the system. Um, and then you have also plug flow reactor, which is basically pipe or rivers or lakes. Okay. All right. So a little bit fundamentals understanding. Any questions so far? This is just a little bit background. All right, so reaction fundamentals. This is something. The first thing you have to remember is the reaction. What reaction means? Reaction means anything that we learn in the chemistry. But it could be also simple things like evaporations. But either way, how do you know? Um, um, okay, there is a question. Can you go back to the type of reactors? Any questions on that? Sharon, you asked me to go back to the reactor, please. Types of reactors. um, where I don't know which slides you wanted me to go. Okay,
Is there any steady state type of reactor?
so here it doesn't say anything what is steady state on steady state. So here you could assume steady state or not steady state. Uh, okay, batch reactor is never a steady state because think of what happens. You are cooking, you dump stuff inside and things will start happening. Our body stomach is a batch reactor. You dump everything and food and then it disappear over time. So that's a batch reactor, okay, unsteady state reactor. But here in the complete mix system, because you are injecting at the same time and things are leaving the system, after a point, if you wait long enough, it achieves the steady state. But it could be both unsteady and steady state. We'll learn that in the couple of examples. It will become more clear. Just learn that unsteady state means things are changing with time. Steady state means all the concentration terms are constant. They are not changing with time. There is no time term anywhere. All right, so a little bit background. Reaction. How do you identify there is a reaction? Well, all you are trying to measure is the concentration of a species that you are interested in. In that example, in news articles, you are interested in the oil or the gasoline or anything that spill. So if you take a concentration of pollutants or you take some samples and measure the concentrations today versus tomorrow, if they are same, then you know that it's a steady state. There is no reaction occurring. But if it's changing, there is a reactions. So that means all you are doing practically is measuring change in concentration with time. So that's we call rate. And that rate, it depends on a lot of times the concentration of pollutant remain in the system. Okay, and it may depends on more of that. So there may be a term here, exponent term, mathematically we write that. So any term here, that's the order of reactions. Okay, and then you have a rate constant. So this is rate constant. So that's the form of reaction we write. And order of reaction is means how much of the contaminant it depends on. Imagine if it is n equal to 1, that means change rate of change in concentration depends on concentrations just to the power 1. But if it is, let's say, 2 second order reaction, what does that mean? It means now reaction rate will increase very rapidly if you have more contaminants, okay, because that means it find each other. So that's the order of reaction. It says how rapidly reaction can occur. If it is more, reaction occur much faster. Okay,
And
and
oh, does the order of reaction, is that a, do we get it from a chemical equation, or can you
uh,
talk?
uh, that's a good question. So usually, it is determined by experimentally because you can have you can write the stoichiometry based on mass balance, but not necessarily in nature that occurs. Because there is other things that can hinder. So usually, order of reaction is something determined experimentally. But if something is given, as a, let's say I say 2a is going to be, okay, that means I'm saying the change in concentrations dA by dt is a to the power 2. Okay, that's very clearly written here, because there are two-way, you need two-way to have the reaction to occur. So that's why this is a stoichiometry, you can just put it there. But not necessarily it's always true, because you have to experimentally verify that. Okay. All right, so higher order reaction means more reactants needed and it goes faster. And think of, order of reaction could be zero order. I didn't write it here, zero order. Um, Zero order means, you don't need the contaminant constant, or it does, the reaction doesn't depend on the contaminant concentrations. Or by reaction, the concentration of contaminant doesn't change over time. One example is think of ocean water, and you are talking about evaporations. Evaporation rate in ocean water doesn't change the amount of ocean water inside the ocean, or the so that means you can practically say it's a reaction doesn't depend on the concentration in the system. Same thing for dissolve, how much oxygen dissolve in water. It doesn't depend on how much oxygen in atmosphere, because even though things are dissolving in water, it doesn't change the concentration of oxygen in atmosphere. So usually, in some cases, you can say zero order reaction. That means it doesn't depend on that concentration. So first order means, depends on one concentrations. Second order means two. Three is three. This power is increasing. But it's very rare to have third order. What it means that you got to have so much to have a reaction occur. That means it most likely will not occur. So most of the engineering equations are either zero order or first order, not second, not third order. That's already too much. Sometimes order of reaction can be fractions. It doesn't have to be 0, 1, 2. It can be zero point 0.5. So I'm just going to write it here. Order of reactions, it can be 0 to some numbers. It can be also a fraction. Okay, it's all determined by experiment. But usually that's something given in your questions. So let's write the unit of rate constant based on the order for reactions. So I'm going to write first order. As I said, I'm asking K. So that's the dC by dt is K. I'm going to write N just to subscript as a way to say this zero or first or second or third, and C to the power N. That's the generic form of equations. Rate of reaction is this. For the first order, or let me write zero order, so that's something I miss here. N equal to 0. So that means dC by dt is, I'm just writing K0 so that it says that this is a zero order constant. And C to the power 0 is 1. So that means this is the zero order rate reactions. That's what I mean. No? Change in concentration doesn't depend on the concentration of the pollutant in the system. For the first order, same thing, dC by dt would be, I'm just writing K1 so that just to show that this is the first order. You don't have to write, no, you can write just K. Then C to the power 1 is C. So that's the first order. Second order, dC by dt is anything. So if I say what's the unit of K0, that's is equal to dC by dt. So what's the unit of C? That's concentrations, whatever the unit. Okay, so I'm just going to write concentration unit. Okay, by time. So that's the unit. Whatever the concentration unit in your system, that's the unit of concentration divided by time. What about here? The unit of K1, concentration cancel out, so it's going to be 1 over time. Okay, so here basically your dimension analysis, what we are doing here. So this will be 1 over time. So anytime I gave you rate constant, I didn't tell you whether it's a first order, second order, just look at the unit. Based on the unit, you can assume, you can say this is first order 0 or 0 order. Again, this is, we can cancel out. So this will be K2 will be 1 over concentrations and time. That's the unit. Okay. Um, Same thing. K3 unit would be this will be 2. So that would be 1 over concentration square and time.
Why do you have time in brackets?
Oh, I just notation. I just put it that way. It is because just to show this is dimension analysis. So this means, let's say your system, you are talking about hour, so that would be hour. Okay. So concentrations dimension could be milligram per liter, or it could be millimole. It could be, whatever the unit is for your system. Okay. Gram per meter cube. So I just write as a notation as a bracket. It's not necessary. You can write just like any bracket is fine. All right, so the idea here is that if you know the notations of units of rate constant, you should be able to say whether it's a first order or zero order reactions. Most of the example problems is either zero order or first order. 99% example is first order reactions. Okay. Second, third order, you really don't get the questions because that's not very realistic or applicable. All right,
Those are
so yes,
those are changes in time and concentration, correct?
which one?
The values are they're changes, correct? Like
Value
initial
of what?
for time and concentration you
Yeah,
use to
so
calculate the.
yeah, yes. So the rate constant is a constant. Okay. So what I write here is just the unit. Okay. I'm not writing. You are not asked to calculate the rate constant because that's why it's called constant. It doesn't change. It's determined by the reaction type. What does change is the concentration. You are going to calculate the concentration. That's why I didn't write here concentration times. It's just the unit of that. Okay. So rate constant is, that's why I say it's a constant. Rate constant doesn't change with time and concentrations. But that's a very good question. So it doesn't change with, but it does change with temperatures. If you have higher temperature, reaction tends to. So K is a function of um, temperatures as well as pressure. Okay. So this is, I'm going to write it here. Temperature, pressure. Usually these are given to you. The K rate constant is always given in all the questions. So you'll use that to solve for C. So let's see the example. The first one is the simplest reaction is the batch reactor. Batch reactor means it's anything dumped in the system and then it's completely mixed. There is no flow in and no flow out. And then you are asked to calculate what's the concentration at different time. Okay. So this is the case where we have the case for the lake where there is a spill, accidental spill. Okay, Johnny asked the question on the last slide, why was he able to cross out DC by C? Okay, so I'm not crossing out. What I'm saying is the unit cancel out. Okay, so unit of C is same, DC, unit of DC is same as unit of C. So I cancel those out. Okay, I'm not canceling the values. Unit is canceling out. So this is just a dimension analysis, unit. Okay. All right. So let's solve it. Batch reactor, no flow. So that means this will be Q in is 0, Q out is 0. There is no flow coming in, coming out. So this is a reactor types. So that means what I'm saying is dV by dt will be all. So the volume cancel. So what it means is the mass balance equation become this. Change in concentration in a system is the change in concentration in the reactor, which is what the system is a reactor. So really we didn't learn much. So now let's solve it. So concentration in reactor change in time is same as it changed because of the reaction. So that means we know that dC by dt would be, for a first order reactor, it will be Kc reactor because whatever system happened inside is the same thing. So That's the system. So dc over dt. So the reaction term what we got is dc over dt is minus kc. That's the simplest way to solve this one. So again, all I did is solve it by dc over c is minus k dt, and then you just have to integrate it. So that's what it happens here. Initial DC system by DC. So you don't write system, that's fine because there is no other concentration term. And then you just have to apply the boundary conditions. At time t equal to 0, your concentration initially is before the reaction, whatever that happened, the spill amount. So that's C initial. Then after time t, you are calculating what that CT would be. Okay. So dc by dt, that's from calculus. Anytime you have to solve this one by integration, this is ln c. Okay. Um, uh, that's the calculus formula. So you got to remember that, or you have to write that. Again, it's an open book exam, so you really don't need to because you have those. But if it is closed book, you write those calculus formula. So dc by c is ln c. So ln c, and then you put those initial c in, and then c at some point. You put those value, then you got that this number. Then again from calculus, ln a minus ln b is ln a by b. Okay, that's the formula. So I apply that formula here, and then I jump in one more step. Um, so that means if I write another equation here, which I jump, ln ct by c initial is minus kt. And then when you change log to exponential formula, that means ct, another term will be ct by c in is exponential minus kt. And then you bring it back here. Okay, so I skip two steps here to get this value. But either way, this is your final answer. Okay, what it means that concentration of contaminant in the batch reactor would decrease from initial concentrations exponentially. So if you plot this graph, I don't know whether it's plot here. Okay, so if you plot it here, the answer would be like this. That's the initial, and then it decreases at a rate, exponential decrease. Okay, so that means if you plot this in a log scale, um, ln c by time, it will be a straight line, and the slope will be, because if you see this one, ln ct by c in equal to kt, so the slope will be minus k. Okay, the y-intercept will be ln c0 or c in. So that's just graphically how you can present this equations. So again, you solve it for a batch reactor. This is exactly like a spill. Imagine you have a spill occur. Initially, everything was not reacting, so completely distributed. There is initial concentrations, and then
Professor? Oh,
yes.
sorry. Sorry. Now I just wanted to make sure that, is this the way we would solve problem 4 from your first slide?
So in exam, you should know how to solve these steps, But a lot of times, for the homework, you should try this method. Should start from the scratch, mass balance. But in exam, I don't expect you to write the mass balance, write everything explicitly. You can say this is the final equations for batch reactor. This is a batch reactor because of this, and the formula for batch reactor is this. So I'm just going to substitute that value. So if you do that one in the exams, it's okay. But homework, I expect you to solve every step because I want you to learn. Because a lot of times you'll not be given all the different complexities. So you got to start with scratch.
Okay, thank you.
We'll solve many examples. In fact, if you see the YouTube video that I solve, I start from scratch. Okay, because that's important solution. For the second order reactions, again the same thing. Now I'm just going to write this one here. dc by dt is minus kc square. So again, solving it is dc by c square is minus k dt. Integrate it. Let me just write this one. C minus 2 plus 1 minus 2 plus 1 equal to minus kt. And this is C initial, this is C time, 0 to t. Okay, let me just write this one. So this will be minus 1. So this will be 1 over C, C in, Ct minus kt. So if you put this value, 1 over Ct minus 1 over C in, it's minus kt. Okay. Anjal asked to go back to the previous slide. Okay, I'm going to go back a little bit. Anjal, do you have questions on this? Or you just need to write it on your note?
Professor,
Yes,
will we be asked to derive those equations or we can just use them?
you don't have to derive.
Okay, thank you.
But again, as I said, a lot of times you have to set up the mass balance equation first, this one. And then you can say that based on the derivation, the answer is this. That way you know exactly where it's coming from.
Okay.
But again, as I said, in the exams, I'm not expecting any derivations. As long as you are comfortable with what the formula is, you can write it down. But you have to say why it is. You have to write your assumption. For instance, here it's equal to 0, it's 0. That's why it turned into this. Here, the integration, you don't have to do all the time. But my suggestion is please write everything in the homework, because that's where I expect you to learn from it. Okay.
So I'm sorry.
Yes.
If we do the ln of the concentration and graph it with time, does that tell us, and we get a straight line, does that tell us that we have a batch reactor, or does that tell us that we have a first order reaction?
Can you say again? I didn't get it.
Because on the side you did the ln of concentration graphed with time versus
Yeah.
time.
Yeah.
So if we get a straight line, does that mean that we are dealing with a batch reactor, or does that mean that we're dealing with a first order reaction?
It means we are dealing with a first order reactor, and it's a steady state. Okay.
Thank you.
I'm sorry. This is not a steady state. This is a first order reactions. All that means. And it could be any reactor. So we'll get to that point. It doesn't have to be a batch reactor. It's a reactor with a steady with a first order.
Thank you.
Yeah, what I would say is don't worry about the batch versus complete mix, all that. That's not important. You will see that time to time. As long as you know what's the meaning of those first order, all that, it should be okay. But there is a comment. The slides are posted under week 2. I always need more time looking at them too, so I have them pulled up next to my Zoom screen. Okay, so yes, that's a good suggestion. If you need more time, because these slides are all uploaded on non-annotated slide, you should show that in the side, so that just in case you don't miss. And again, because this is all recorded, if you miss writing something, I would say that give some space and just let's move on, unless you need some actual time for understanding. Okay. All right, so I'm not expecting this derivations. You will never use it. I'll never ask any question on second order or third order. So I'll just put it there so that you know that you have a way to solve it. The one last thing before we think of, a lot of times we ask for half-life. What does that mean? Half-life means, imagine you have how long it takes for the concentration of contaminants to become half of what is you started, the time. Okay, so that's the time. So for a first order reaction, let's solve it. First order reactions, the solution is this. Ct equal to C0 minus Kt. That's the solution for first order reactions. So my question is, you just have to apply these boundary conditions. Okay. So at T equal to T half or half life, C equal to C0 by T. So that means if you put this number at C equal to C0 by 2, T half. Okay, so if I substitute time t equal to t half, which is this conditions if I apply, C become 1/2 of initial concentrations. So that means it cancel out. So if I take that means 1 by 2 is e to the minus k t half or t 0.5, or another way to say is 2 equal to e to the power k is become positive, so k t 0.5. Now if you take log, natural log ln2 is k t half 0.5. So that means you can write t half for a first order reaction is ln2 by k. Okay. So a lot of times if I ask, half, what's the half life? You could just use this equation, just some substitute 0.693 divided by k. Okay, that's the just only apply for half life for first order reactions. And you could exactly do the same thing by solving for the zero order or everything else. Okay, just see the expression for the concentration term, these equations, and then substitute that boundary conditions. So these are all going to be clear if when we start solving examples. So let's solve the first example questions. What is the concentrations of a benzene in a pond of 1000 meter cube water after a week if 10 gram of benzene is filled into the pond? This is exactly example similar to what we just learned in the news articles. So let's write there is a pond. You spill amount of benzene you spill is 100 gram. Okay. And I ask you what is the concentration would be in the pond. The volume is given 1000 meter cube. And I ask what the concentration would be after a week. So I give you time, 7 days. Now question is, does the concentration of contaminant change with time? Is there a reactions? Yes, there is a reaction. It says benzene is decayed in a pond at a rate of 0.1 d. So K is 0.1 over day. So now I didn't tell whether it's a first order or second order or third order reactions or zero order, but I give you the unit. Unit of K is 1 over time, and you know that that unit is for first order reaction. So I just put it K1. That means just to indicate that this is a first order reactions. That means this dC by dt is Kc. All that means in that. Okay. I'm just going to take them out, just simplicity. I don't have to type multiple letters. Okay, so that's the first order reactions and everything else given. And it asks the concentrations. I ask you what is the concentration after 7 days. Okay, would be. So for that, you got to answer it. So no, you know that this is a batch reactor. The solution is this. So I just wrote the solution directly. I didn't try to solve it. So let's answer it. But the point is, you know the time, t equal to 7 days, k is given, ct you are calculating, this is what you are calculating. What you don't know is the initial, what's the initial concentrations? Well, it's given in a different way, you just have to calculate it. So what is initial concentration? C initial is whatever the amount of mass you added by volume of water that's in the pond. So initially what you add is 100 gram of benzene by volume is 1000 meter cube. But I asked what's the concentration in milligram per liter. So that's why you have to change that into unit to something milligram. So I'm just going to write that here, 100 gram per 1000 meter cube, so that I can change. 1 gram is 1000 milligram. And then you know that 1 meter cube is 1000 liter. Okay. So once you have the conversion, 1000 cancel, gram cancel, meter cube cancel. So that becomes whatever that number in milligram per liter. So that's 100 by 1000 is 0.1 milligram per liter. Okay. So that's the initial. So if you put this one here, 0.1 milligram per liter exponential term, K is 0.1 per day times T is 7 day. Okay, they cancel. So this exponential term is unitless. So the answer is 0.1 times exponential 0.1 milligram per liter. So that number you can calculate, whatever that number is. Okay. So again, everything else is given. You just have to calculate the value. Any question? There is a negative term somewhere. Oh yeah, yes, here. There is a negative term. The reason
So
is
it should be
concentration
0.7,
changes
right?
there. Second,
It should be negative 0.7, right?
negative 0.7. Yes, minus Kevin. Yes, you are right. There is a. I can make this typo. Thank you. Oh, this is 0.1 times 7 is 7. I'm glad this is recorded. That way people know how easy to make mistakes. Okay, all right. So let's solve another questions. Example quiz. Oh, I have example quiz. All right, so there is example quiz. So let's just do, there's a poll. So I'm going to start the poll. Okay. You know what? I will put the quiz later because there is some question here that you can answer without. So I'll put that from after we cover some of those things. So we'll be back to this later. Okay.
Professor,
Yes.
can you please go back one page just for 1 minute?
Okay.
Okay, thank you.
Yeah, there are 153 students in 153. That's true. No, by the time you said it, it's a 151. People left. They just want to prove earlier wrong. Now it become 150. All right, so okay, so let's start with next questions because we have a couple of questions and we'll solve those answers. Anything we can cover here, I'll put that on. Put those on the recording. All right, so complete mixed flow reactor or CS. Some in your textbook it's right CSTR. Okay, so it's all same. What it means that things are mixing and flowing in and out of the system. Okay, that's all it means. Because it's a completely mix, all that means is you have ability to say that the concentration of contaminant in the system is same as what's leaving the system. So C equal to C out. That's the only thing. You know, mathematical, all that means is that's the same. You can take contaminant concentration at different times. You should be able to that. Concentration change in reactor depends on reaction rates, volume of reactor, all that stuff. Okay, so let's see that solutions. So mass balance, again, what's coming in the system is what's coming leaving the system, because this is there is no accumulation of flow rate or the volume doesn't change, so that's why you could say. So this is the mass balance for the water, and it's the first order reactions. Usually we solve for first order. Let's stick with that now. So dC by dt equal to kc out. Okay, because another way to say is dC by dt is minus kc. So let's solve it now. So dC by dt of a system is equal to everything that's coming in minus everything that leave the system plus everything that's being reacted. And as you notice here, I always put plus sign because I don't know yet the reaction is creating or destroying the contaminant, and which is integrated into this equation here. That negative term is saying that it's being destroyed. So you start with plus sign, then you put those negative sign as part of the reaction rate. So I put all the system here. So this is your the final mass balance equation, because your one thing is coming in, one is leaving the systems, and this is the reaction term. Okay, this is in, this is out, and this is what's the change in contaminant concentrations in the system. So now to solve it, you have to, you can solve it because first of all, you can write the, if I write the mass balance equation, that will be VdC by dt of a system would be C in Q minus C out is same as C contaminant in the system because that's a mixed reactor. So Q minus VKC. Okay. So now you have, this is your final mass balance equations. All I did is change the concentration term based on the mixed reactor equations. So now you see usually given C in, that's the concentration that's coming in is given to you. Flow rate is usually given to you. Volume is given. Rate of constant is given. The only thing that's missing here is the C. So to solve for C, you have one equations and one unknown, you can solve it. And that's basically differential equations. So we'll learn that how to solve it. So that depends on whether it's a steady states or unsteady states. Let's solve it for steady states. Steady states means concentration doesn't change with time. So that means this first term will be all zero. Okay. So that's what we did. This term is zero. So everything right hand side is become equal to zero. When you put this value, and then you solve for C out or the C. Okay. Rearrange the equations. So I'm just write this one, rearranging it, C in Q. If I take C out, this will be Q plus VK equal to 0. Then you C out Q plus VK is C in Q. Then you solve for C out. This one you take this one down here. So that's how I skip couple of steps here to get this point. So that means your concentration of contaminants leaving the system is a function of what's coming in, what's the flow rate, what's the volume, what's the rate of reactions. Okay, so all these factor depends on that. And if you rearrange it, you divide flow rate on both sides, you get this. You can rearrange it this way. Why it is important? Because volume of our flow rate. If you see what is the flow rate, is the rate of change in volume over time. So this unit of this one is actually time. Okay, if you do the dimensional analysis, this is an order of time. Okay, and this is special because all it means is how long it takes to empty or not empty, replace the liquid in the system. So we call this hydraulic retention time or residence time. So this time we call residence time. What does that means is, physically what it means is, imagine you have a reactor with lots of water and you are continuously flowing a different liquid. All I'm asking is how long it takes to replace the liquid which what is originally in the reactor. So that's the average amount of time a liquid is going to stay inside the system. And that's why it is important, because the longer it stays in the system, the more reaction it will be affected by. So that means your effluent concentrations will decrease because you're spending a lot of time inside the reactor. So let's see now theoretically what does that mean. Your concentrations C out, your goal is to decrease because that's what you want to react. So this decrease if your C in decreases, because that's the numerators. And if your K increases, that means if you're reacting much faster, your concentration in the effluent will decrease much faster than your time. If your residence time increases, the C out or the effluent concentration will decrease. Well, how you decrease the residence time or increase the residence time? Make the reactor much bigger. So this means you either make the volume much bigger, so that means it stay longer, or inject liquid lot slower rate, so that is stay longer. So these are that. Okay. So conceptually, this is what it means. If you inject at slower flow rate, your reaction will be much more efficient because spend more time. Or if you make a big reactor, it's you'll react much more liquid or much more contaminants. Or if you have a reaction time much higher, how do you increase the reaction rate? As I said, reaction rate depends on temperature. So that means you may be applying heat here. That's why you cook. When you cook, you apply heat to increase the reaction rate. Okay. How do you decrease the C in? Well, that's not depends on you. It's just you are saying that take remedial action so you don't get lots of pollutants. So usually C in is not in your control. That's something is happened. That's accident happened. Okay. All right. So the CMFR is done. Let's solve for the. This is something I already explained it, so we don't need to explain again. All I'm saying is how the concentrations out depends on all different terms. Okay, C in 1 plus K V by Q. So I'm saying that plot the concentration as a function of reactor volume. So if you C out versus volume, how that equation would look like. So if you do that one, you'll get a as you increase the volume, the reaction out will decrease. So it will be something like 1 over V scale. So if you plot it, you'll see that's how it look like. So it means that if you increase the volume more and more, you are treating a lot more pollutant. That's all it means. Okay, so for unsteady state, because we did solve this one because of steady state, dc by dt equal to 0. For unsteady state, we cannot say it is 0. So if that's what I did it here, unsteady state, I put this one equal to this, and then I say that what if I ask that source is removed? That means C in equal to 0. Then you can solve this one. I'm not going to solve it here right now because there are multiple examples given exactly same thing. So let's not think about it. I'm saying that if there is an unsteady state, there are a way to solve it. So let's try that in an actual example. So this is an example from a previous textbook or the reference book. So let's solve this one so that you learn how to solve CMFR. Okay. Okay, CMFR, continuous CSTR, these are all same, just means it's completely mixed reactor. Just think of, it doesn't really mean anything more than that. Okay, before entering the underground utility vault to do repairs, a work crew analyzed the gas in the vault and found that it contains 29 milligram per meter cube of hydrogen sulfide. So there is an underground utility. Imagine a room, that's a reactor. Okay. The utility crew, when they go in and they found that there is a contaminant exists. So that's initial time. At time t equal to 0, C0 or C initial concentration was 20 milligram per meter cube. Okay, that's all it means. Because the allowable exposure level is 14 milligram per meter cube, the work crew began ventilating the vault with a blower. So their objective is to decrease the concentration to 14 milligram per meter cube, because that's what allowed. So how they do it? They blow. So that means there is some kind of flow. The work cube began ventilating with a vault with a blower. The volume of the vault or this room is volume is 160 meter cube, and the flow rate of that air that they are blowing, that system is leaving the system, the flow rate is 10 meter cube per minute. How long it will take to lower the hydrogen sulfide level to a level that will allow work crew to enter. So how long means I'm asking how that time would be when the concentration of contaminants will become 14 milligram per liter. Assume the manhole or that vault works like a CMFR, completely mixed reactor. So that means when you hear that one, that means you can assume the C in the system is same as C out. Okay, so C in the reactor is C out. Okay, that's all you are trying to write that. That hydrogen sulfide is non-reactive, means there is no reaction term. So non-reactive means no reaction term. Okay. So let's write the equations. Okay. V dc by dt is what's coming in. So that will be Q C in minus Q C out, which is equal to C. That's why, right? And then there is a reaction term. Um, that's the normal way to write it. But as I said, this is non-reactive, so this one we can call 0. And then you know that when you are blowing, you are not actually blowing any contaminant. There is no, you are blowing the free contaminant free air. That's what is written here. That means this C in equal to 0. Okay. So now all you have is this term. V dc by dt is minus QC. Okay, you just have to solve for it. Well, there is no way to solve and no space, so I'm going to solve it here. We did it so many times, so I'm just going to write the final answer. dc by dt is minus q by v dt. Yes, any questions?
I have a question. Why doesn't it equal 0? Because isn't it 0 minus QC times 0?
Oh, is which one? If
Oh, that's
the
plus. My
term
bad.
is 0, there is a plus term here. Okay.
Thank you.
Yeah, it's not marked. I put the sign opposite way. So let me make it clear. There's no plus here. Okay. So when you solve it again, the same thing. The answer is ln C is minus q by v t, and you just have to put the boundary condition. So this is initially C0, then you are calculating for C and time t equal to 0 to t. So this will be ln C by C0. If you do the exact same thing, I'm just not going to do every step now. So that means C is C0 e to the power minus q by v t. Okay. So now you know the C0, that's given 20 milligram per liter. You know the Q, that's given 20 meter cube per minute. Volume is given in meter cube, and time is then a reaction. Time is given how much? How long? Oh, you are actually calculating time. I'm sorry. So let's not bring it here because that's easier to solve here. Okay, because you are asked to calculate time. So time would be minus volume by Q if you take the other side, ln C by C0. Okay. Volume is given, flow rate is given, concentrations are given. The final concentration was 14. Initially is 20. So you just plug all the number. So time would be, I'm just going to write it here in a different ink so that you can see that that's the final answer.
Dr. Mohanty?
Yes.
Isn't the initial C 29 milligrams per meter cubed, not 20?
Oh, yes. I am not surprised that I have so many typo now. Yes, it was C0 is 29. It's written here. I had that 20 written. I don't know why.
When
Okay,
you
so yes.
Professor, see that C in it's goes to 0.
No,
Why is that?
I'm not saying it's 0. I'm just writing a different notation. So you can write this is a C in. Okay. Usually C0 is the constant term, so I always write that that way. It's not. It's a notation.
When we plug the value of the flow rate into Q, do we take into account the negative sign because it's an outflow?
No. It's already there. That negative sign is it's part of the mass balance equation. If you see over here, there is a negative sign here.
Okay, thank you.
So this will be minus volume is let's say 160 meter cube. Flow rate is 10 meter cube per minute. And just so when you do any homework, you have to write the units. Otherwise, I don't know what you are doing. Okay. Ln C is C is 14 milligram per meter cube by 29 milligram per meter cube. So these are cancel out. So you'll have a number, okay? So whatever that number would be, so this will be time. So if you see meter cube cancel out, this concentration cancel out, 1/minute. If when it goes, the answer will be in minute, whatever that number is. Okay.
Professor,
Yeah.
when I was asking for the CEN going to zero, I was meaning for the equation on the right, bottom right, where it
Yeah.
says v of the derivative of c over dt, and then you put equals to q, and then the CN, that one's the one that you mark that goes to zero. That one was kind of like my.
Did I write something wrong somewhere? I don't think I understand. I was. Can you repeat your question?
Yeah. On the bottom right part.
Yeah. Yeah.
Uh. Oh, okay. I
Oh,
think Victor is answering the
yeah,
my.
what I'm saying is that term zero because there is no reactions. Okay, there is a reaction term that's supposed to be there. K something, I say that zero. And same thing in the bottom Q C in, there is nothing coming in. The C term is zero. So let me write this one. What it means that when you are blowing air, this C in equal to zero. Okay, that makes it easier. And then there is no reaction, no reactions. That means any reaction term is zero. So that's why there are two zero that goes here. One is C in. That means when you're blowing air, you're not blowing any contaminated air into the system anymore. So C in initial amount, not initial amount, the things that coming in is zero. And there is no reaction. That's why there are two. Okay.
Yeah, thank you.
All right. So let's see. We have few more minutes before we call it a day. The reason is there is still another type of reactor. So this is plug flow reactor. So we have to, I will say I will work until slide number 27 before we say end, because then there are a lot of examples and I will, so you see there are a lot of example here, example 1, 2, 3, 4, 5, 6 or 5. I'm not going to solve it. The reason is I solved it already, the same similar questions. You should be able to solve on your own. So you will try. Only after you finish trying, this week, I will probably upload around on Thursday or Friday. That way you can see your solutions. And by the way, these examples are from book. So the solutions are in the book. I'll just explain it. This is also in the book. This is also in the book. So these are all in the part of the book. This is not in the book. So this is a different questions from a previous the reference book. So I'll just solve it. So try all these questions on your own after this class. This is also a relatively quiz question. So I'll not explain it today. You will be able to answer those just to understand. Then we'll explain in the recording. So there are 4 slides to go. So let me finish that. So this is one of the questions that you solve the steady state reactions or unsteady state reactions, whereas input rate is not really varying because you are blowing air, but you are not adding anything onto it. What if that same thing, that you are blowing air, but that air has a lot of pollutants? So that means by the time workers know the concentration of contaminant in the home will increase, because now you are blowing not just clean air, you are blowing way higher concentration than you thought. So if that happened, what will be how long it will take before you realize that there is a steady state, means the concentration will increase and it will remain at a certain point. So you want to know that. And there is also reaction, different type of reactions. Things are like, you have a reactor which has, there is a reaction that removing the contaminant. There is also a reaction that is actually creating contaminant or the generations coefficients. Um, so if you have all these things, it's become a very complicated system. So you can still solve it. This is already solved in the textbook. I'm going to do it, just explain you how to do it. And that way you can go back to the textbook and you should also see detailed steps. Okay, so let's write the mass balance equations. Again, same way, volume times concentration change in the system is whatever coming in minus whatever going out plus minus reaction term. Okay, so that's what you're doing. The accumulation rate in the system is what is the input rate because of flow, output rate because of flow, and then there's the reactions. And here there are two reactions. One reaction what actually create the uh, contaminant, the destroy the contaminant. Another is producing. There is a typo here. It should be plus because you are creating generation. You are making a stop. Okay. So let's write the reaction rate. It's a first order reaction rate. So that means dC by dt is minus kdc. Okay, that's the amount of contaminant reacting in the system. But at the same time, there are also pollutants which are supplying the system. Okay, so that is a zero order reaction. So this is kg. The general amount of contaminant is dumping into the system. It's a zero order because whatever your system, you're assuming that it's dumping so much that it doesn't really matter. The amount of stuff, it doesn't depend on concentration in the system. You can dump as much you can, irrespective of how much inside the system. So this is the reaction term. Okay. There is a plus sign here because that's creating more mass, or this is adding more contaminants. You know what? I should not use this. So if you plug those values here, you got this mass balance equations. So now you have to solve it. So now imagine what you are saying is if you keep adding the new contaminants after a point, long time, that's why set T equal to infinity, your effluent concentrations would become some value. Okay, that's whatever that value, that would be C infinity. Okay, just a notation, whatever that value is after a point. So think of what is that number would be. So if you continuously add system, there is always some contaminants coming in. So things are coming in here, and then you are producing something here, this, and then you are also destroying some amount. The remaining amount will leave the system here. So because of that, if you add steady state infinite time, that means it's a steady state. The things will not change over time. C infinity, you can solve it. So if you solve this one at steady state, dc by dt, that infinite time would be 0. So that means you can solve for everything else. QCI minus QC infinity, because you are talking about what happens after a long time. I'm just putting a notation here, nothing else. So equal to 0. Okay. So that means you can solve for what that infinity is, means what is that concentration would be after a long time. Okay. So that would be, if I write this value here, PQCI plus VKG Q plus BKD. Okay. Just rearranging the equation, you will get this number. So I'm just going to keep doing the same mistake as the CI. Okay. So if I ask you after a point, what would be the concentrations if you continue to blow it out and it become equilibrium or steady state? This is the answer. That's easy to answer because it's just a solving both sides. But what's the difficult to answer is how long it will take for the system to reach that number. So I'm asking here the time. It's basically same example we solved here, some point, wherever. I think we solved some example like that for time. Yeah, here is the time value. You solve this one. It's basically you are solving the same thing again. So let's derive that equations. Okay. So you have more term here. That term doesn't have any reaction, but now you have a reaction term. Okay. So let's write it. V dc by dt is QCI minus QC plus VKDC.
Since you're solving for C infinity and that slide you're just on, when you're moving all your variables over, is it supposed to be, can you go back a page?
Second,
I think you're negative sign on the last slide.
let me see. I think I make some mistake somewhere. So let me finish writing this one, then I'll go back. KGV. Is there anything that I missed, some negative sign somewhere?
Should you have a negative sign next to QCI because you have changed negative VKD to positive, so you're switching sides, right?
This will cancel out. So if you see there are two negative sign here, I just basically bring to the other side, so it should not be any. So this is correct answer.
Okay, thank you.
All right, so we're going to solve it. So we are solving for C. We are solving for C, so that you can calculate what would be for time. Okay, so let's basically we are solving for C. So there are one equation, one thing. So usually when you solve for C, it makes it easier to solve it if you put every constant or concentration term in one side, everything on other side. Okay, so let's write this one in a way that will be allow you to do that. So QCI plus KGV, this is no concentration inside, there is a constant term. So I'm just going to combine them together. Then the other one would be, if I take C common, it will be Q plus VKD. Okay, all I did is just group them together, and then this is the same thing. So now what I'll do is I will, if you see C infinity is this, so for that reason I'm going to divide this term, okay, so that C term will be remaining same. So if I divide this term for both sides, it should not change the answer. Okay, so all I did is so that I can isolate that variable. So now what it becomes is this, whatever the constant, I'm just going to, if you see this number is C infinity. So this is C infinity minus this is C. Okay, this cancel out. So that's C is volume divided by Q plus BKD dC by dt. Okay, so it become much simpler. Okay, now what you do is let's again the same way like we did, C infinity minus C, let's substitute as Y. Okay, so that means D, if you take derivative of both sides, D, if you take the derivative of left side, C infinity is a constant, so that will be 0. So this will be minus dC by dt is same as dy by dt. So if you plug this value here in these equations, you'll get dC by dt is minus dy by dt times this term here is equal to y. So now it's become a lot easier for you to solve. So let me call this one as a some constant so that I don't have to keep writing this term here. So this will be let's call this one as a b. It's just a constant. So the b is this. Okay. So that means you got simple equation. So this will be dy by y is dt by b. Okay, and then you can solve it. It's already solved it, so that will be it will be the answer would be y equal to y0 because times e to the power minus t by b. Okay, you solved it before, so I just, if you go for that route, you'll do it. So the idea is, you solve these equations, then all you are solving is time equal to t. So you are saying that if I put c equal to c infinity, what will happen to time? So that's how you are going to solve it. So I'm not going to do that because this is exactly given in the textbook. So you look for that answer, so you know the process, so that you know how to solve this one. I think, because we have less time remaining, I would just recommend you to look at the textbook because it solve it, and you so that you should have a answer. But basically, what is that? By graph, you can present this way. If the time increases, initially you start with something, you start adding more and more stuff, it will increase. After a point, it becomes steady state. That becomes infinity. And that's the time you are calculating here. I would say that go and look at the textbook, and if you have any difficulty in that questions, ask me on a campusware, or try to solve the questions in one of the example question, because similar questions are given there in a more specific way. Actual numbers are given, and that way you will see whether you can solve or not. This is the last two slides. Let's go through this quickly. This is basically a plug flow reactor. Plug flow reactor is basically a batch reactor moving. So you're not going to solve any different new ways. That's why it's a lot easier. So let's think of what is reverse and wetland and pipe. The assumption here is that water is moving. The entire water column is moving in the river from one location to another. Okay, as it moves, there is no mixing of that volume from the left and right. It's all mixing in the vertically. So essentially, plug flow reactor is a batch reactor moving at certain speed. That speed is the flow rate, or the volume divided by time, or the flow rate. So when you think of plug flow reactor, think of this is a batch reactor, but that batch reactor is moving at certain speed. That means you can solve this one by just using the same equation that you solve as a batch reactor. So that's why I wrote the mass balance reactor. For plug flow reactor means you take one plug. Okay, plug means that one column, and you are solving for that what concentration of contaminant inside that plug, because it's not mixing from laterally. So if you do the mass balance equation, there is no flow because that plug is independent. It's not really mixing, so there is no flow coming in out. It's just moving at certain speed. So that flow rate is now become part of the how quickly things are moving in the channel. Okay, so that's why you put those value flow rate 0, because we are solving only for that plug, that little thing. So that's why it become like a batch reactor. So all you are doing here is you are solving for the concentration in that one water columns at certain time. And when I ask, what time is on locations, the location is a function of time, because how long that plug it takes to go to that locations. Because you know the flow rate, you know the area of the channel, then you can calculate that time or the distance. So the let's say the velocity of water is a flow rate divided by area of the channel. Okay, if you know the velocity, you know the distance. So distance, how long it takes for that time to be there. So that means the time would be distance by velocity. So distance is given usually because you are asked at what location in the river. That distance is usually given, and the velocity of water in the channel is basically flow rate divided by area of the channel. So that will be Q by A. So what I mean is the time is usually given. If I ask you what's the concentration of contaminant at locations, I give you distance. If I give you distance, I give you basically the time values. And that time values come here. So that means, you have a batch reactors. That batch reactor is moving. You know the concentration of contaminant in a batch reactor at different time. And this time become a distance formula. So this will be C initial or whatever the time location, initial location, exponential minus K. T is the distance of that location divided by Q by area. Okay? Or the velocity, if you know the velocity of water. So anytime you are talking about contaminant concentration in a river at different location, you can use these equations. So we call again plug flow reactor. The basic assumption is that the water column is moving, okay, and inside the water column, the reaction is taking place. So it's like a batch reactor moving. So you don't have to solve any new equation. You just plug the value directly. So anytime you have a plug flow reactor, river, wetland, pipe, you just use this equation. Start with these equations, put the value and get the answer. Really, there is nothing else. So I show you that the time is a function of distance and area and flow rate. So these are all things that I already mentioned. Let's solve a question so that you can see how it is done. All right, so an accidental spill of benzene in a stream flowing at 1000 liter per minute with a cross-sectional area is 10 meter square. So the area is 10 meter square. And the flow rate, the amount of flow that coming in is 1000 liter per minute. Okay. So that means I know the velocity of water. So the velocity of water is what? Velocity is Q by area. So 1000 liter per minute divided by area is 10 meter cube. But no, meter cube you can change to you can change the liter to meter cube. So 1000 liter is 1 meter cube. So that way it's cancelled out. So that would be meter square. Area is meter square, 10 meter square. So that means it will be the numerator will be 1 meter cube per minute. Denominator is 10 meter square. So that will be 0.1 meter per minute. Okay, that's the velocity of water. That's how fast it's moving. Okay. The concentration of benzene increase at a locations to 500 milligrams. So at one location, at distance d equal to 0, the concentration is 500 milligram per liter. That means that's where you just dump all the stuffs. And the rate is given. Rate constant is 0.1 per day. Now I ask you what would be the concentration of benzene after 1 kilometer from the location where it was spilled. So I give you the distance. At d equal to 1 kilometers, I ask you what the concentration would be. Okay. So if you know, this is again mass balance equation. So C equal to C initial times, if you see this value, exponential minus K length times area times flow rate. So everything else is given. We really don't have to do anything, all this velocity calculation. So you see initial is 500 milligram per liter, exponential minus K is 0.1 per day, length is 1 kilometers. That you have to change to meter because everything is meter. So 1 kilometer is 1000 meter times area is 10 meter square divided by the flow rate is, we already converted the flow rate. So let's say 1000 liter per minute and 1000 liter is 1 meter cube. So that's all units are constant. So again, just to show you, this is the meter. This is kilometer, kilometer cancel. This is meter Q over on the top. The denominator, all the meter cancel. Liter, liter cancel. So this is minute and this is day. So that's another thing. You have a day and you have a minute. So you have to change to a day. So I'm going to change that to, 1 day is how many minutes. So 24 hours times 60, 1 hour is 60 minutes. So this is minute. So that means you have also changed minute to day. So this thing cancel out. So this will be unitless, this entire term inside this bracket. So you'll get some number. Okay, so I think this is how you can solve it. Solve all the questions on the examples. So okay, what we learned? We learned 3 type of reactor. Batch reactor means there is no flow coming in and out. Things are changing because of contaminant reactions. Then the complete mixed reactor, batch reactor or CSTR or CMFR. These are basically you have flow coming in and out, and you have also some reaction happening. And in that system, if you have a steady state, you can solve it. If you don't have a steady state, you can still solve it, like a differential equation we use. And the PFR, which is river, for pond, and anything else, it's a batch reactor, just moving. So that means you use the formula like here, and you just have to plug those values. So this is just a conceptually same as batch reactor. The only difference is moving with time. That's how you include your distance term there. So with this, you can solve any mass balance equation in environmental engineering, particularly nature. So that's all we learn. And this is the equation for zero order, first order, second order. I would say that don't worry about all that. This is just for your cheat sheet. If you imagine you had exams and you want to finally write the residence mean retention time formula or the concentration effluent, this is what we solve for. C formula for zero order reactions for different type of reactor. You have the solutions here given. So you just plug that value and solve it for. So anytime if I give you a question, as long as you know what type of reactor it is, whether it's what type of reaction rate, you can just plug the value. So for instance, this will be ideal plug flow reactors with the first order reactions. If I gave you zero order reactions, you should be able to use this term. So you can just pick those values and solve it directly. All right, now there is a time for quiz. What you learn? So what I'm going to do is I'm going to stop the share here because I will share the poll. Okay, so this is again voluntarily. I'm not asking you for launch the poll. Okay, so there are 3 questions here. What is the unit of first order rate constant? Okay, so you just have to answer those in. So let's start. Let's start answering the first one. Once you finish first one, look at the second one and the third one. Let me see if I can. I'm going to share the screen for the poll itself. If I can. I don't see how I can share the screen of the poll itself. Because that window is missing here. But you see the screen. I'll share the screen at the end. The first question is easy. What is the unit of first order rate constant? I'm just asking what's the dimension would be. Okay, so you'll answer that one. And the second one I ask is which reactor can handle shock? Is that CMFR, the one where you have a constant volume and then you just mix together stuff, or a plug flow reactor like river? And the third one is which reactor requires less volume to decrease the effluent concentration to the same value? So these are all the answers you can answer by mathematically by looking at the expressions. But what we'll learn today is how to answer those questions conceptually. So give whatever answer, because I don't really care about what answer you gave. I just want to know how many of you just thought. So I cannot share the answer until you guys give your, just pick any number, whatever comes to your mind. Okay, we'll learn that. Okay, you have 75 or 79 students, 80 students right now. Respond to it. You have total 97 students. I'll give you another 1 minute to just respond any one of those answers. Then I will discuss it. All right, so 87 students, that's 91% voted. So I'm just going to end the poll so that I can share the screen. Okay. Actually, some you have 10 more seconds to answer because I know that there are 5 students who still thinking. Again, just whatever comes to your mind. Okay, I'm just going to share the answers and then we discuss. This is just so that you can learn later. All right, I'm going to end the poll now, 89 students. And now I'm going to share the screen. Okay. Let's see, how do I share this entire screen? You know what? I'm going to share the entire my desktop. That's the only way I could share the. Okay. This is your result. That's why you can see. The first question what's the unit of first order rate constant? That means dc by dt is kc. So c cancel out. So the answer is 1 over time. So 83 or 93% student got the right answer. So which is correct.
We're seeing your desktop, like your calendar and stuff.
You're not seeing the screen?
No, we're seeing your desktop, not everything that's on your.
Oh, I see. Okay, so I don't know how to share that poll. Okay, I say I'm sharing your poll, sharing the poll. So hopefully you see the screen on your window. Okay, I don't know how to share it, but I just want to say that 83% or 93% student thought that 1 hour time is the right unit of first order rate constant, which is correct. So just check again, this is just what you learn. So I'm not expecting that you all got it right. Just you can go back and see. Let's see the second question. Which reactor can handle shock or sudden increase in concentrations? So it's a tricky question, but think of what does that mean? The difference between CMFR and PFR. So let me share the now the question on the iPad. That way it's a lot easier to see. But just to get your idea is, the second and third questions are roughly the answers are 50-50. In the sense people are 50%, almost 47% thought something else, 53. So it's kind of divided. So let's see how to solve, because there is one correct answer. So I'm going to share the screen of my iPad so that you can see the. All right, so which reactor can handle shock, means sudden increase in temperature, or the sudden increase in, so think of plug flow reactor versus this reactor. So this is Q in, Q out. Okay, this is CMFR. Okay, and the plug flow reactor is like this. Things are going in, you have a batch that's moving. Okay, so think of what happens. Imagine you have added some amount of high concentration of contaminants. What will happen is, because it's a completely mixed system, it has a volume term here. What it does, it dilutes the system very quickly because it's mixing. So that's why it is very easy for a CMFR to dilute the system so quickly that before even reaction happen, the concentration decreases just by sake of the dilution. Whereas CMFR, there is no way to dilute because there is no mixing going on from left to right. So that batch reactor has the contaminant. So that's why you see there's a dilution that's decreases the peak very quickly. Whereas for CMFR, this is all still the peak. The concentration decrease is only because of reactions. Whereas CMFR, initially the concentration will decrease because of the dilution itself, because it's unsteady state, right? Because you are just suddenly increase the concentrations. So that's why, because of the right answer would be CMFR. It will be easier to handle the shock increase. The reason is it dilute the contaminant peak, which is the shock. Okay, so this is the shock. Shock means it just suddenly things rise very quickly. Okay, because of dilution, this will does it. The second is which reactor require less volume to decrease the effluent concentrations. So the answer is this is PFR. I will tell you why. Okay, so again, same way. The answer is the very similar thing. What the reason? So why you need less volume? Or another way to say is PFR require less volume to treat to decrease the concentration of contaminant to the same level. Let's say this is C in and this is C out. Um, and this is C out, C in. So the question is which if your goal is to have the same decrease in concentration, same C out, which require less volume? PFR require less volume. That means more efficient. The reason is, think of what reaction is. Reaction is depends on, if you have first order reaction, dC by dt, Kc, the reaction rate depends on the concentration of contaminants. Okay, if you have high concentrations, the reaction rate will be much faster. Things are reacting very quick because the contaminant will find each other, the reactant will find each other more efficiently. So think of where the concentration of contaminant is high when this get to the system. Same reason, the moment you dump something in here, it become diluted. So the entire system is diluted such a way that it doesn't find each other. So the reaction rate is very low because of the dilution factor. Whereas in the batch reactor, everything is in the block flow reactor, that reactant is not mixed left and right. So they are more efficient at reacting at the same time. So the reaction rate is much higher in that column versus in that entire CSTR or CMFR. That's why it takes a lot of larger volume to treat the same amount or to decrease the same concentrations. So again, this is the answer is same. Dilution makes the reaction less efficient for CMFR. Okay, whereas PFR there is no dilution because that column is moving, it's not mixing with the side. So that means the reaction rate is much faster in the PFR. That's why you are decreasing the concentration very efficiently within the small volume because you're not diluting it. Okay, but mathematically you can see the equation. If you plug the equation volume and all that, you'll get a different volume. In the PFR, you need only 69 liter for a certain degree of change in concentrations, whereas in CMFR you need 100 liters. All right, so that's all. Everything we covered. These examples are for yourself to do it for your practice, or 5 questions. So please solve those. And I think we should be able to answer most of the questions. Again, I gave you all examples. So everything we solve in this class is already in the example. The examples are not very different. So try solving those. I also uploaded the YouTube solving some of the similar examples. So you have already like 8 or 9 examples. And TA is going to explain some more examples. So the next homework questions, which will be mass balance, should be able to solve any mass balance question from now on. Okay, steady state, unsteady state, reaction, no reaction, doesn't really matter. Start with the basics, start putting the value, and the differential equation will be what I gave you. There is no, we are not talking about second order reaction. So that means you are solving the same linear equation all the time. Okay, the techniques I show you, whenever you cannot separate the variable, assume that C infinity, plug the value so that you transform into something simple equations. So using this, I would say that any environmental engineering problems with a mass balance, you should be able to solve. Okay. All right, so we learn everything that we need to. Next class we'll learn about energy. Okay, we didn't learn about mass. We learn about mass balance. We didn't learn about energy balance, temperatures, heat transfer, all that. So that will conclude all kind of mass energy balance chapter 1. And from next week we'll actually go to the individual type of problems. Okay, so this is kind of a basis for entire class. Okay, everything that you learn this week will be reapplied again and again for specific system. We'll go to groundwater, we'll apply this one. We'll go to wastewater, we'll apply this one. So whatever you learned in these first 2 weeks are going to keep coming back again and again, but in the same form. So you should be able to solve any problems, any wastewater treatment, any problems, just using the same concept. So this 2 week of class is very important because of that. All right, in a way that if you don't take any class anymore, you just have to, from now on, you'll just to understand the system. You're not understanding the concept anymore because all you already understood by end of this week. Okay, you will apply to the many systems. All right, see you 2 o'clock. I'm hungry. I hope you have your lunch. See you next week, or not next week, on Wednesday.
Thank
you.
Can I ask you?
Yes. Ask question. I'm not going anywhere. If you have question, ask.
From the chemistry homework, question 1D, the one where we're converting for the calcium carbonate.
Yeah.
Do we have to use equivalent weight for that?
I don't know the question off my hand. Let me open the question itself.
I had a difficult time with that one as well.
Okay, let me open it so that way.
We're getting like split numbers in some of our chat.
Okay, let me share the screen. The question. Okay, so which question?
1D.
Okay, so milligram per liter calcium carbonate. So you got to have equivalent weight.
Okay, so it's not a 1-to-1 ratio.
Let me see, sodium bicarbonate. Because you have one bicarbonate has the same as one carbonate, same number of carbonate is conservative here. So you don't need to, the way I see this one here. So try this one. I could not think why you need it, but let me see the solution later because I didn't solve it.
Okay, thank you.
Okay, or ask this question on CampusWare. I'll write it there. Okay.
Professor, I think you said that you sent an email.
Yeah.
To get into Campus Wire.
Yeah.
Was that like this weekend or?
No, last week. So let me send another email. Let me send another email just in case. But if you just for the code is 3636. If you don't, just go CampusWare and start that. Okay, 3636.
Right. Thank you.
Okay. My son is barging in, so okay.
Dr. Maharaj.
Yes.
I was just wondering if the annotated notes were going to be uploaded later.
Yeah, I'm going to upload right now.
Okay, thank you.
Entire video and as well as the annotated slide right now. It'll take a while because it's a big file. So look for another 1 hour from now. It should be all uploaded.
Okay.
Okay. See you all on Wednesday.